In this video, we'll apply the second-order ODE to solve real-life problems. There are two classical types of problems we can tackle. The first is the oscillation caused by spring. The second is the oscillation caused in the electrical circuits. Let's do a quick recap of what we have covered previously. The simplest example is the free oscillation. In the spring system, you have a weight attached to the spring. If initially the weight is displaced away from the equilibrium position of the spring, then you let go, the weight will undergo free oscillation, assuming there's no friction, there's no energy lost. In an electrical circuit, it is equivalent to the circuit having one capacitor connected with the induction coil. If there is a current running through this circuit, it will again oscillate between the capacitor and the induction coil. After free oscillation, we also discussed the damped oscillation. In the spring system, you have a weight, you have a spring, and you also have a dashpot. In the equivalent electrical circuit, you have the capacitor, induction coil, as well as a resistor. Getting the system even more complicated, we can have the forced damped oscillation. In the spring system, you have the weight, the spring, the dashpot, as well as an external force. The force can be expressed as F0 multiplied by cosine omega t. From the expression, you can tell the external force has its own amplitude and frequency. In the equivalent electrical circuit, you have the capacitor, the induction coil, the resistor, and now you have an additional external voltage. The external voltage is also periodic and has its own amplitude and frequency. The expression is slightly different from the external force in the spring system. In this case, it's E0 multiplied by sine omega t. You will see why it is sine very soon. Since resistance is R, inductance is L, capacitance is C, this circuit is also called RLC circuit. In this video, we'll focus on the electrical circuit. The way to describe the RLC circuit mathematically is to look at the voltage drop at each component. Across the resistor, we know the voltage drop is simply R multiplied by I, where R is the resistance, I is the current. For the voltage drop across the induction coil, it is equal to L multiplied by di over dt, where L is the inductance. For voltage drop across the capacitor, it is equal to Q over C, where Q is the charge, C is the capacitance. Current is simply just dQ over dt, then Q can be expressed as integrate IT dt. Having this information in mind, we can write down the voltage drop across the entire circuit. So on the left-hand side of this equation, we have Ri plus Li prime plus 1 over C integrate I dt, which is equal to the voltage from the source. Differentiate this equation once. We have Ri prime plus Li double prime plus 1 over Ci equals to E0 omega cosine omega t. Slightly rearrange the above equation. We'll have Li double prime plus Ri prime plus 1 over Ci equals to E0 omega cosine omega t. And this expression tells us it is a non-homogeneous second-order ODE, something we covered in the last video. And also, looking at the right-hand side of this equation, it's very similar to what we have in the spring system. From the last video, we learned we have the general solution as well as the particular solution for the non-homogeneous second-order ODEs. The general solution is also called the homogeneous solution, which can be denoted as H. For the particular solution, it can be denoted as IP. The homogeneous part of the solution tells us the intrinsic property of the system. The particular part solution tells us the oscillation determined by the external force or the external voltage. Let's look at the particular solution first. We'll set IP as A cos omega t plus B sine omega t. Then the first derivative of IP prime is equal to omega multiplied by minus A sine omega t plus B cosine omega t. The second derivative, IP double prime, is simply omega squared multiplied by minus A cos omega t minus B sine omega t. Substitute IP prime, and IP double prime to the equation we had before. You will have cos and sine terms. Let's write them out. We have two unknowns, A and B, and two equations. We can solve A and B. A is equal to minus E naught S over R squared plus S squared. B is E naught S over R squared plus S squared, where S is omega L minus 1 over omega C. Now, let's look at the homogeneous part of the solution. From the previous videos, we learned the homogeneous part of the solution can be expressed as C1 e to the power lambda 1 t plus C2 e to the power lambda 2 t, where lambda 1 and lambda 2 are roots of the characteristic equation. Writing down the characteristic equation, which is lambda squared plus lambda over L plus 1 over LC equals to 0. Lambda 1 can be expressed as minus alpha plus beta, while lambda 2 can be written down as minus alpha minus beta, where alpha is equal to R over 2L and beta is equal to 1 over 2L square root R squared minus 4L over C. After that, the solution is simply IH plus IP. I will not expand these solutions here. Let's look at one example from the RLC circuit. Assume the capacitance is 10 to the minus 2 Faraday, the inductance is 0.1 Henry, the resistance is 11 ohm, and the external voltage is 100 sine 400 t. Find current, assuming that I naught is equal to 0 and Q naught is also equal to 0. We have the RLC equation, Li double prime plus Ri prime plus 1 over Ci equals to E naught omega cos omega t. Plug in the numbers for the inductance, resistance, and capacitance, and the voltage. Looking at the homogeneous part of the solution first, writing down the characteristic equation, you can get lambda 1 equals to minus 10 and lambda 2 equals minus 100. Then the homogeneous part of the solution is simply C1 e to the power minus 10t plus C2 e to the power minus 100t. For the particular part of the solution, S is equal to omega L minus 1 over omega C. That gives you 39.75. With the value for S, you can calculate A and B. A is equal to minus 2.3368 and B is equal to 0.6467. Satisfying the initial condition, you will get the current as a function of time. Let's have a closer look at the solution to see what we can learn from it. In this current equation, as t increases, the exponential component decreases dramatically and quickly approaches 0. What this tells you is the intrinsic oscillation behavior diminishes and the external frequency dominates as t increases. Before wrapping up today's video, Let's do a quick comparison of the RLC circuit to the spring system. For the RLC circuit, Li double prime plus I prime plus 1 over Ci is equal to E naught omega cosine omega t. For the spring system, My double prime plus Cy prime plus Ky is equal to F naught cos omega t. Doing a very quick comparison, you can see the inductance in the electrical circuit is very similar to the mass of the weight you have in the spring system. The resistance you have in the circuit is the same as the resistance you have in the spring system. And 1 over C is the same as the spring constant. Last not least, the current I is analogous to the displacement in the spring system. This is the last video we have on the second order ODEs. Starting from the next video, we'll look at even higher order ODEs.